All right, welcome back. In this lesson, we're going to learn how to determine the most common oxidation state of main group elements. Boy, that's a mouthful, isn't it? Um, the oxidation number or oxidation state of an element is often very similar, or in fact even the same as the element's most common charge. So we'll be kind of talking about these two things interchangeably. All right, so at the end of this lecture, you should be able to, if given any element from the main groups of the periodic table, tell what the most common oxidation number or charge would be for that element. All right, so oxidation numbers, charges. This all goes back to valence electrons. And if you remember in the previous lecture, we talked about valence electrons and how easy it was to determine by looking at the periodic table how many valence electrons an element has. All the elements in group 1 have 1 valence electron. All the elements in group 2 have 2 valence electrons. Group 13, they have 3 valence electrons, 14, 4, 15, 5, etc. And then when you get all the way over here to the right, the noble gases, group 18, they have 8 valence electrons. And as we learned in the last lecture, 8 is the maximum number of electrons, valence electrons, that any element can ever have. So how does this tie in with oxidation numbers or charges? Well, we're going to start by bringing back the fact that elements want 8 valence electrons. Elements want 8. Even if they don't have 8, that's what they want. That's what makes them most stable. So elements want 8 valence electrons. So the noble gases are sitting pretty. They're in group 18. They all have 8 valence electrons. That makes them very, very, very stable. But if you look, as you go down the periodic table, all of these elements have 17. That means they're just 1 valence electron shy from being where they want to be. They have 7 valence electrons, group 17, they have 7, and they want 8. So they all want to get 1 more electron. On the other hand, if you go all the way to the other end of the periodic table and you look at group 1, all of these elements only have 1 valence electron. So their valence shell is their outer shell of their electron cloud is almost empty. So it's much easier for them to ditch the electron from their outer shell, and then the next shell down, the next energy level down, becomes the highest energy level, and it's full. So all of these elements, they want to lose 1 valence electron. So over here, these guys want to gain 1 electron. And over here in this column, these guys all want to lose 1 electron. And by gaining or losing 1 electron, groups 17 and 1 will get 8 valence electrons, and that makes them very stable. The only problem is when atoms gain or lose electrons, it's messing up their charges. So let's take fluorine, for example. Fluorine right here. Fluorine's atomic number is 9. That means it has, as an atom, it has 9 protons and 9 electrons. And if you remember way back at the beginning of the class, we learned that protons are positive and that electrons are negative. So for fluorine, it's got 9 as an atom, 9 protons, and it's got 9 electrons, which means that its charge as an atom would be 0. Now, we can call it a charge because that's what it is. It's its electrostatic charge. But oftentimes in chemistry, instead of talking about charge, we talk about either its oxidation state or its oxidation number. They're not quite exactly the same thing because charge is a real property, and oxidation numbers are more like bookkeeping, and you're going to be learning a lot about them in the second semester of this course. But for now, we're going to kind of use them interchangeably because they're very often the same thing. So a fluorine atom with 9 protons and 9 electrons has a charge or oxidation number of 0. Well, we just found out that a fluorine atom, since it has 7 valence electrons, would like to gain an electron. So what would these numbers look like if that happened? Then all of a sudden it would still have 9 protons. It's fluorine after all, and that's what makes it fluorine. But if it gains an electron, it's going to have 10 electrons, and electrons are negative. And so look at what happens. 9 minus 10 is negative 1. And so when fluorine gains the electron it wants, so that it can have 8 valence electrons, it becomes minus 1. And so the most common oxidation state or oxidation number for fluorine is minus 1. Okay, let's go to the other end, and we're going to look at lithium. Lithium, as an atom, has 3 protons, so plus 3, and 3 electrons, so minus 3. So again, as an atom, its charge or oxidation number would be 0. But lithium, to become more stable, wants to lose an electron. So if lithium loses an electron, it's going to still have 3 protons, but it's going to lose an electron. So now it's going to be minus 2 because it lost an electron instead of gaining one like fluorine did. So 3 minus 2 is positive 1. So the most common oxidation state or charge of lithium is going to be plus 1. All right. So we have fluorine wanting to gain valence electrons over here, and we had lithium wanting to lose valence electrons over here. Think about that for a second, and then look at oxygen. It's in group 16, which means it has 6 valence electrons. It wants 8. It wants a full shell. So it has a choice. It can either gain 2 electrons, or it can try to lose 6 of them. So which do you think it's more likely to do, gain 2 or lose 6? It makes a lot more sense that it would gain 2. And so if it gains 2 valence electrons, here's oxygen. It normally has 8 protons and 8 electrons, which is a charge or oxidation of 0. If it gains 2 electrons, it's going to have still 8 protons. It is oxygen after all. But if it gains 2 electrons, then it's going to be minus 10 for the negative charge, and that means its overall is going to be negative 2. So if it gains 2 valence electrons like it wants to do, then oxygen's oxidation number is going to be minus 2. Its charge is going to be minus 2. All right, now we're almost to the point where we can kind of detect a pattern. But before we jump to any conclusions, let's just look at one more. We'll look at magnesium. I jumped down a line. It doesn't really matter though. Magnesium down here, its atomic number is 12. So magnesium, if it's 12, it has 12 protons, and as an atom would have 12 electrons for an oxidation number of 0 or a charge of 0. But it's in group 2, which means it has 2 valence electrons. So it has a choice. Does it try to gain 6, or does it try to lose 2? And just like it was easier for oxygen to gain 2 electrons to get to 8, it's going to be easier for magnesium to lose 2 rather than to try to gain 6. So it's going to lose 2 valence electrons, and then that's going to give its next lower energy level that'll be full of 8. So if it's losing 2 electrons, it'll still have 12 protons, but it lost 2 electrons, so now it only has 10 electrons. And so that means it's going to have an oxidation number of plus 2, or a charge of plus 2. So that means that magnesium's most common oxidation number, most common charge, is plus 2. So now it looks like there might be a pattern developing, and in fact there is. As we follow this across, nitrogen is in group 15, and their most common oxidation number is negative 3, for all of the same reasons that we just went through with fluorine, oxygen, magnesium, and lithium. And aluminum right here, gallium and indium, they're metals, and their most common oxidation is +3. They want to lose the 3 valence electrons that they have so that their next lower shell is full of 8. That gets us to this group right here, carbon, silicon, germanium. They've got 4 valence electrons. They're right in the middle. And so they're just as likely to lose those 4 electrons and have a +4 oxidation number as they are to gain 4 electrons and have a -4 oxidation number. Now, a good rule of thumb to follow is to use the metalloids to kind of guide your thinking here in terms of whether these things are going to be positive or negative oxidation numbers. So if we look at where the metalloids are at, and if I outline them on here, and we've already learned in this class about metals, nonmetals, and metalloids. But here are the metalloids. I'm outlining them in purple. A pretty good rule of thumb is that things that are to the left of the metalloids are going to have positive oxidation numbers or charges, and things that are to the right of the metalloids are going to more often have negative oxidation numbers or charges. So if you just kind of follow this pattern that I've outlined for you across the top here, it should be very, very easy for you to determine the most common oxidation number of any element in the main group of the periodic table. So look at sulfur. It's in group 16, so its most common oxidation is going to be -2. If you come down here to potassium, it's in group 1, so its most common oxidation or charge is going to be +1. It's that easy. And if you want to, you can go ahead and write these oxidation numbers right across the top of your periodic table in your planner. As always, if you have any questions about anything that I covered in this video lecture, feel free to ask me in class, and thank you very much for watching.